I want to start today by asking you to participate in a quick, well, a completely silent experiment.
Okay, I'm intrigued.
Yeah. Wherever you are right now, whether you're commuting, doing the dishes, or just sitting on your couch, I want you to think of a sentence.
Any sentence.
Literally anything at all. But here's the catch. Don't say it aloud. Don't even move your lips.
Just think it.
Right, just think it. Actually scratch that. I want you to really scream it right there inside your own head. Give it everything you've got entirely internally.
It's a strange feeling, isn't it?
It really is.
That volume, that intensity, but completely contained within the walls of your own mind. Now, I want you to hold on to that feeling. Because if you were sitting in a lab at Stanford University right now, specifically, as someone they refer to as participant T16, you wouldn't be the only one who just heard that internal scream.
Wow.
The computer would have just typed that exact silently screamed sentence right out onto a screen in front of you.
With no talking.
No.
And no typing required. Just pure, unfiltered thought to text. And that is exactly what we're getting into today. Welcome to our deep dive into the source material, the internal monologue, decoding the architecture of thought.
It's such a fascinating topic. We are exploring a massive paradigm shift happening right now in the world of brain-computer interfaces,
Yeah.
or BCI.
Our mission today is to really understand how science is moving past the physical body and tapping straight into the mind. But to get there, we kind of need to establish the baseline, right?
Right. To appreciate the magnitude of this shift, we have to look at where this technology was even just a few years ago. The old BCI technology was strictly about motor skills.
Meaning physical movement.
Exactly. You'd have a patient imagine moving their left arm. The interface picks up the neural signal from the motor cortex, and it translates that into moving a cursor on a computer screen.
Which is, it's basically like trying to type with a joystick.
That is a perfect analogy.
It's functional, and obviously it's an absolute miracle if you have no other way to communicate, but it's incredibly clunky.
Oh, very clunky. Revolutionary for its time, absolutely. But fundamentally, it was just mapping physical movement. The goal today is to understand how science is moving past that joystick.
Tapping directly into the voice inside our heads, and our musical expressions, and even our visual imaginations.
We're transitioning from the translation of spatial commands to the translation of abstract linguistic thought. It's a completely different neurological landscape.
Okay, let's unpack this. Because the specifics of the Stanford study are a massive technological leap. They aren't tracking those basic motor functions anymore.
Right. They aren't asking participant T16 to imagine flexing a bicep just to select a letter on a screen.
They are tapping directly into the internal monologue itself, the very voice you just used to scream that sentence in your head.
And the sheer technological leap there cannot be overstated. By intercepting the internal monologue, they've bypassed the motor system entirely. They're going straight to the source code of human cognition.
And the mind-blowing stat here, the one that really changes the game, is that this thought-to-text translation is operating at a staggering 74% accuracy in real time.
What's fascinating here is why moving from spatial commands to linguistic commands is such a monumental leap in decoding the brain.
Because spatial is just vectors, right? Up, down, left, right.
Exactly. You're dealing in binary, easily definable vectors. But when you decode the brain's architecture to pull out actual words, you're dealing with an infinite combinatorial space. Language is messy.
Extremely messy.
It's heavily associative, and it happens incredibly fast in the brain.
Let me stop you there, though, because that 74% accuracy figure is incredible, but it does make me wonder about the other 26%.
The error rate.
Yeah. If I'm thinking a sentence, is the computer just throwing out a completely random word when it messes up? Or is it a specific kind of failure?
That's the perfect question. The errors aren't usually random at all. They often come down to phonetic similarities or the associative messiness we just mentioned.
Phonetic similarities, so like words that sound alike.
Think about homophones. If your internal monologue says, I need to write this down, the neural firing for the concept of write, W-R-I-T-E, can look remarkably similar to write, R-I-G-H-T.
Oh, because the brain is retrieving the phonetic sound of the word alongside the actual concept.
Exactly. The BCI has to rely on complex language models, kind of like predictive text, but it's running on raw neural data. It's trying to map the phones that you're internally vocalizing.
Though sometimes it just misinterprets where one word ends and another begins.
Or it grabs a semantically related word instead of the exact one you thought of. To hit 74% accuracy on the fly despite all that noise means we're no longer just guessing at signals, we're reading the dictionary of the mind.
It fundamentally changes what it means to communicate for someone who is locked in. But here's the thing. Stanford solved the dictionary. But simply getting the words right isn't enough for true human communication.
No, it's not.
A perfectly accurate dictionary transcript is incredibly robotic. If I get a text from a friend that just says, fine, I don't actually know what fine means unless I know the context.
Right. The subtext.
Exactly. It's about getting the vibe.
And getting the vibe is an incredibly accurate way to frame it. Scientifically, what we're unpacking here is prosody.
Prosody.
Yes, prosody means capturing the rhythm, the pacing, and the pitch of the thoughts. Not just the raw text. It's the difference between saying, oh great when you win the lottery, and oh great when you get a flat tire.
The text is identical.
The syntax is identical, but the prosody carries the actual emotional meaning.
Which brings us to the UC Davis study, because they realized that text without tone is only half the battle. They aren't just capturing the raw text of the inner voice.
They're capturing that prosody.
Tracking the rhythm and the pitch. And there's this incredibly moving example in their research where an ALS patient, someone who has lost the physical ability to speak, was literally singing melodies through the neural interface.
That detail is profoundly significant. Think about what that abolishes. For decades, the public image of these devices has been that robotic, monotone style.
We all instantly picture Stephen Hawking.
Exactly. That technology was life-changing, but it relied on discrete inputs. You select a word, the machine says the word at a fixed pitch.
Stripping away the entire emotional tapestry of how we talk.
Right, but singing a melody. That requires the interface to process a continuous, fluid, variable pitch in real time. The UC Davis team proved they can isolate and decode the neural correlates for pitch and rhythm.
They are picking up the actual musicality of the internal monologue.
Yes. And when you think about the application of that, it restores actual, nuanced human expression to those who have lost it.
To be trapped in a failing body, but still be able to project the specific melody of a song you're thinking of or convey the actual warmth in your voice, it's getting the humanity back into the machine.
It proves our internal monologue isn't just a silent ticker tape of text running behind our eyes. It has sound and pitch and emotional weight.
So we're mapping the words at Stanford, and we're mapping the music of our thoughts at UC Davis. But what about the pictures? Here's where it gets really interesting.
The visual element.
Yes. The Japanese team in our source material is tackling visual imagination. They are currently using the AI tool Stable Diffusion to literally paint pictures directly from human brain scans.
And since we know how Stable Diffusion works with standard text-to-image prompting, the wild part here is the application. They are basically treating the human occipital lobe as the prompt window itself.
The brain is the keyboard.
Exactly. You aren't typing a cat on a skateboard. The prompt is the raw fMRI data coming from a human brain, while the person is simply visualizing something.
Turning the human brain into the ultimate AI prompt. And the future predictions here are just wild. Researcher Yu Takagi noted that while they aren't recording actual dreams yet, he believes it could happen in just 10 or 20 years.
10 or 20 years.
Just a decade or two until you can wake up, pour some coffee, and watch a video playback of the dream you just had.
It feels like pure science fiction, but the trajectory of the technology absolutely supports that timeline. Visual processing in the brain is incredibly robust.
Because the same pathways light up when we imagine something as when we physically see it.
Right. The AI's job is just to take that blood flow data from the fMRI and reverse engineer the image that caused it.
But the translation isn't perfect yet, which brings up this hilarious quirk from the research. The current AI they are using is considered a genius at music, but it absolutely choked when trying to draw a simple salad bowl.
A salad bowl.
Yeah, it completely failed to visualize a salad bowl from the human brain scan.
If we connect this to the bigger picture, that salad bowl problem explains why visual brain scans are immensely complicated. Translating the abstract nature of visual thought is a completely different beast than decoding text or musical pitch.
Why is that? Because music is more structured.
Exactly. Musical pitch is based on mathematical frequencies. It scales predictably. An A note is 440 hertz.
It's a defined, measurable thing. But a salad bowl isn't just one thing.
Right. Visual thought relies on reconstructive processing. When you visualize a salad bowl, are you seeing the exact photorealistic shape of a specific bowl you own in your kitchen? Or are you seeing the abstract concept of a bowl?
Or the individual overlapping leaves of lettuce.
The gleam of the light hitting a cherry tomato. Visual thought is heavily layered, chaotic, and deeply subjective.
So the AI is looking at this fMRI data thinking, I can give you a perfect symphony because I understand the math, but I have absolutely no idea what to do with this subjective pile of leafy greens.
Precisely. The AI is looking for clean lines and defined edges, but human visual memory is often a blurry, impressionistic mashup. You don't just see the bowl. Your brain fires off associations about the texture of the wood, the taste of the dressing, the spatial awareness of it sitting on a table.
It's a massive jumble of overlapping neural data.
Which makes perfect sense why a machine trained on clean digital images struggles to parse the messy reality of the mind's eye.
It is oddly comforting to know that our brains can still stump the most advanced AI with something you'd find at a buffet. But looking at all three of these studies together, it paints an incredible picture of neurotech.
The synthesis of this research is breathtaking.
We started with mental joysticks. Then we saw the leap to translating our silent internal words into text at 74% accuracy.
Decoding the dictionary of the mind. And then we saw the UC Davis study, allowing patients to sing their thoughts, moving past that robotic monotone.
And finally, the Japanese researchers giving us the imminent possibility of recording dreams, systematically decoding the architecture of thought across text, sound, and image.
But as we move from basic communication to the literal extraction of our internal experiences, we really are fundamentally redefining the boundary between the self and the outside world.
And that is exactly what I want to connect back to for you, the listener. What are the real-world implications here? Because we are rapidly entering a world where the concept of privacy might mean something entirely different.
It's a structural change to privacy.
Up until now, your mind has been the ultimate impenetrable sanctuary. You can retreat into your internal monologue, scream a sentence silently like we did earlier, and nobody else can hear it.
But the reality of this new era is that if our literal inner thoughts, melodies, and visions become readable data, that inner sanctum is technologically accessible.
It's a monumental medical breakthrough, obviously. But what does it mean for your inner sanctum to be accessible?
It exposes the vulnerability of the human mind to technological mapping. It dissolves the boundary of where you end and the network begins.
It changes the very nature of keeping a secret.
It certainly does.
Yeah.
But amidst all this profound analytical power, there is still that stubborn, chaotic element of human cognition that defies simple translation.
The salad bowl.
The salad bowl.
Right.
And that leaves us with a final provocative thought for you to ponder on your own.
Let's hear it.
If artificial intelligence can decode our complex internal monologues in real time and map out the intricate musical melodies we hold in our minds, but it totally fails to visualize a simple salad bowl, what does that tell us about the messy, chaotic, and beautifully unmappable nature of our own visual imaginations? Are our most mundane thoughts actually the hardest ones for machines to understand?